Stellar black holes can be up to 20 times greater than the Sun's mass, but are relatively small. They exert a powerful gravitational pull on other objects. Every large galaxy contains a supermassive black hole at its center. Scientists think black holes formed in the early universe, after the Big Bang. Stellar black holes form when the center of a very massive star collapses in upon itself. Scientists can see the effects of a black hole's strong gravity on stars and gases around it. When a black hole and a star are orbiting close together, high-energy light is produced. Welcome to the space station. Before we proceed, kindly subscribe to our channel and hit the bell icon to stay updated when we release new videos. Without further delay, let's dive in. The Sun will not become a black hole, but it will die in billions of years. After that, it will become a red giant star, a planetary nebula, and then a cooling white dwarf star. White holes are the exact opposite of black holes, and they are regions in which space-time flows inexorably outwards. If a crew attempts to enter a white hole, the sheer force of the gamma rays would destroy them and their ship. White holes. What we know about black holes' neglected twins. White holes are theoretical cosmic regions that function in the opposite way to black holes. Just as nothing can escape a black hole, nothing can enter a white hole. White holes were long thought to be a figment of general relativity, born from the same equations as their collapsed star brethren, black holes. More recently, however, some theorists have been asking whether these twin vortices of space-time may be two sides of the same coin. To a spaceship crew watching from afar, a white hole looks exactly like a black hole. It has mass. It might spin. A ring of dust and gas could gather around the event, horizon the bubble boundary separating the object from the rest of the universe. But if they kept watching, the crew might witness an event impossible for a black hole to belch. It's only in the moment when things come out that you can say, "Ah, this is a white hole." Physicists describe a white hole as a black hole's time reversal, a video of a black hole played backwards. Much as a bouncing ball is the time reversal of falling ball. While a black hole's event horizon is a sphere of no return, a white hole's event horizon is a boundary of no admission, spacetime's most exclusive club. No spacecraft will ever reach the region's edge. Objects inside a white hole can leave and interact with the outside world, but since nothing can get in, the interior is cut off from the universe's past. No outside event will ever affect the inside. Somehow it's more disturbing to have a singularity in the past that can affect everything in the outside world. Einstein's field equations hit physics like a tsunami in 1915, and theorists are still sorting through the wreckage. Beyond describing the force of gravity, his hypotheses also brought a paradigm-shattering message about the nature of reality. More than a rigid backdrop, space and time bend and fold along with the mass of stars and planets. That insight sparked a race to calculate just how much abuse space could take from the matter that drifts through it. Within a year, physicist and astronomer Carl Schwarzschild found the first exact solution, opens a new tab, to Einstein's equations, calculating how spacetime curves around a single ball of mass. In his answer, lay the seeds of what physicists today call a singularity, a spherical mass shrunken down to an infinitely dense point, wrapping space around it so tightly that the region pinches off from the rest of the universe. It forms a no-man's land whose event horizon fractures the link between cause and effect. Black holes, the most famous singularities, are regions of space so warped that no exits exist. The outside universe can influence the inside of a black hole's horizon, but the interior can't affect the exterior. When mathematician Martin David Kruskal opens a new tab extended Schwarzschild's black hole description in 1960 to cover all domains of space and time, his new picture contained a reflection of the black hole singularity, although he didn't realize its significance at the time. Later, as black holes entered the vernacular, a natural term emerged for their theoretical twins. It took 40 years to understand black holes, and it's only recently that people have been focusing on white holes. While general relativity describes white holes in theory, no one knows how one might actually form. A black hole cordons off its bit of space when a star collapses into a tiny volume. But playing this video backwards doesn't make physical sense. An event horizon exploding into a functional star would look a bit like an egg unscrambling itself. A violation of the statistical law demanding that the universe gets messier over time. Even if large white holes did form, they probably wouldn't hang around too long. Any outgoing matter would collide with the matter in orbit, and the system would collapse into a black hole. A long-lived white hole, I think, is very unlikely. For a while, white holes seem to share the fate of wormholes, mathematically permissible contortions of spacetime, likely prohibited by reality. But in recent years, some physicists have brought white holes back in an attempt to save their darker siblings from an unseemly death. Ever since Stephen Hawking realized in the 1970s that black holes leak energy, physicists have debated how the entities could possibly shrivel up and die. If a black hole evaporates away, many ask, what happens to the internal record of everything it swallowed? General relativity won't let the information out, and quantum mechanics forbids its deletion. How does a black hole die? We don't know. How is a white hole born? Maybe a white hole is the death of a black hole. The two questions join nicely, but you have to violate the general relativity equations in the passage from one to the other. Rovelli is a founder of quantum loop gravity, an incomplete attempt to move beyond general relativity by describing space itself as built from Lego-style particles. Guided by tools from this framework, he and others describe opens in new tab, a scenario where a black hole grows so small that it no longer obeys the common sense rules of stars and billiard balls. On the particle level, quantum randomness takes over, and the black hole could transform into a white hole. Such a microgram-sized white hole, being similar in mass to a human hair, would have none of the gravitational drama of its black hole ancestor, according to Haggard, but would hide a cavernous interior containing the information of everything it had swallowed in its previous life. Too small to attract orbiting matter, the white hole might remain stable enough to eventually spit out all the information accumulated by its forerunner. In this picture, white holes would one day come to dominate the universe, after the stars have burnt out and black holes have withered. Any observers then could easily detect the objects as relatively large particles, Haggard speculates. But those days are countless trillions of times the current age of the universe in the future. It's the craziest timescale I've seen in physics. Alternatively, the aftermath of a white hole may exist everywhere. To black hole physicists, the Big Bang's explosion of matter and energy looks like potential white hole behavior. The geometry is very similar in the two cases, even to the point of being mathematically identical at times. Cosmologists call this picture the Big Bounce, and some seek characteristic white hole features in the universe's earliest observable light. Rovelli also wonders if violent radio bursts represent the cries of theoretical mini-black holes left over from the Big Bang as they make an early transition into white holes, although this explanation appears increasingly unlikely. The universe may not contort itself into all the shapes general relativity allows, but Haggard thinks physicists should follow this rabbit hole all the way to the end. Why wouldn't you investigate whether they white holes have interesting consequences? It may be that those consequences aren't what you expected, but it would be foolhardy to ignore them. That's all I have for you guys for today. If you liked watching this video, please make sure to click the like button, subscribe to our channel, and click the bell icon so that you may be notified when we upload a new video. Thanks for watching.